Hello, everyone, and welcome back to Unit 2 of Regents Chemistry, which is Atomic Concepts. Today, we will be talking about the history of atom. So, the discovery of atom, as we know it today, was a progression, which means this is not the type of the atom that we know today was not the atom that we knew, let's say, 100 years ago. Just like the discovery of DNA or any other major scientific theory out there. So many scientists contributed to the development of the present day atomic theory of what we know about atom today. So each proposed model of atom was based on the models that developed prior to it. So today we'll be talking about all those different types of models that finally gave us the model that we believe in today. So the first scientist that we will be talking about today is John Dalton, and Dalton said that atom is the smallest particle of any element that can ever exist. And he basically gave four postulates for his theory, which is called the Dalton's theory. So his first postulate said that all matter out there is made up of atoms, which are like tiny particles. And he said that if you're looking at atoms of same element, then those atoms are going to look together, which is absolutely correct. And if you're looking at atoms of different elements, then they're going to look different. So this is what Dalton said, but he did not quite explain that. So today, based on everything else that we know about atom, it makes sense, and we can definitely go ahead and prove this. But at that time, this is all that Dalton said. He just predicted this and put this up in his theory. And then he said that when compounds are formed, we have different elements combining in fixed proportions, which means if we are looking at water, water is H2O, which means we have two atoms of hydrogen and one atom of oxygen combining together to make water. If you change that, if you take out a hydrogen and just have one hydrogen and one oxygen combining together, that is not going to be water. It's going to be a hydroxide ion. If you add another oxygen and so now you have two hydrogens and you have two oxygens, that is now going to be a hydrogen monoxide. So still not water. So whenever we are making compounds, we are combining different elements and they have to be combined in fixed proportions to make the specific compound that we want to make. And then finally, Dalton said that atoms are indivisible, which means they cannot be divided into further parts and they cannot be broken down or created whenever we have a chemical reaction. So the next scientist that came along the way was J.J. Thomson, and he did this experiment called the cathode ray tube, and he gave us the electrons, and that's something uh, that kind of proved Dalton's theory wrong, that atom is not the smallest thing out there because atom does have subatomic particles and one of them was electrons. So cathode ray tube is basically like a sealed glass tube that contains a gas and has like separated metal plates which are connected to external wires that pass electric current through that. So then the opposite charges just go towards the opposite ends. So J.J. Thomson view like a negative ray passing through. So he said that, well, atoms do have these negative particles called the electrons. So J.J. Thomson gave us this model of atom called the plum pudding model. And this model basically said that we have like this positive pudding and the negative particles, the electrons, are just embedded everywhere in that positively charged pudding, just like a chocolate chip cookie. So just imagine your cookie part as the positive pudding, and then the chocolate chips in there are the electrons. That's what J.J. Thomson presented as the model of atom. He said this is what atom looks like. So J.J. Thomson's theory was disproved, or his model of atom was disproved by the scientist named Rutherford, and he performed this gold foil experiment that he used to kind of say that Thomson's model is not quite that complete. And this gold foil experiment, guys, is very, 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 very important because Regents is obsessed with gold foil experiments. And make sure you guys know what this experiment was about, what Rutherford did, and what were his conclusions. So basically, as you guys see in this picture, we have like the source of alpha particles, which are positively charged particles. And what he did was that he was bombarding those alpha particles, the positively charged particles, on a gold foil. He observed that some of the particles were just like passing straight through, some of the particles were being scattered in different directions, and some of them were deflected back. So this is what his observations were that most of them just went straight through, but some of them were deflected back, bounced back, or scattered. And his explanation for that was that the particles that were able to pass straight through was because there might be a lot of empty space in the atom, and those particles were, because they were not coming in contact with anything, there was nothing stopping them or nothing kind of hindering their way. They were able to pass straight through, and go hit the other end of the foil. However, those that were bouncing back or those that were scattering, they were most likely hitting a positive center in the atom. This is what Rutherford said. So basically something that looks like this. We have this beam of alpha particles that is going straight through. Now when it's passing through that empty space, it is able to go through. If it's hitting that positive center, it is deflecting back. Uh, if it's kind of not directly hitting the positive center, but kind of like it's closer to that, it's kind of colliding with it, then it can be scattered. Um, okay, so this is what Rutherford was trying to explain. So based on his conclusions and based on his goal for the experiment, the model that he gave us was um, this nuclear model, because he said that we have this positively charged nucleus in the middle of the atom, and then we have electrons surrounding that nucleus. Now, Rutherford was super close to the model of the atom that we believe in today. Now, there were just some things missing, which the future scientists then kind of clarified, and they worked more on that. But Rutherford did a great job in getting us very close to the model in which we believe in today. Now, the next scientist in line was Niels Bohr. And he said that the problem with Rutherford's model was that when electrons move in like around the nucleus, what could eventually happen is that if they are at like a very, very high speed, and they can eventually gain speed, then they start losing their energy. And when they lose energy, there will be a time when those electrons would have just collided with the nucleus and the atom would have been gone. So Niels Bohr said that, well, electrons are not just out there, just revolving with whatever energy they have. They actually revolve in fixed orbits, and those orbits have fixed energies. And this model was called the planetary model because it looks very similar to our solar system. We have the sun in the middle, we have the planets revolving in their orbits. So that's what Niels Bohr said, that we have the nucleus in the middle and we have the electrons revolving around the nucleus. Uh, but the thing is, his model was fundamentally incorrect because then there was another scientist that came after Niels Bohr and he said the electrons do not quite move in the fixed orbits. In fact, there's something a bit more than that. So let's talk about what that next scientist said. So that scientist was Schrödinger, and he gave us the wave mechanical model of atom, which is what we believe in today. Even though for convenience, we sometimes, like whenever we have to draw the atom by hand, we also use the Bohr model because that also makes sense. But wave mechanical model basically just said that because by this time scientists had talked about the wave mechanical motion and the wave mechanical nature of matter. So they said that matter and energy can basically behave as both waves and particles. So they said that, well, electrons do not quite revolve around the nucleus in those fixed orbits. In fact, there is like this electron cloud, which is like the space around the nucleus in which electrons can potentially be found. And within that electron cloud, there are these, like, this is what electron cloud looks like. And within this cloud, there are like specific places which are called the orbitals. And each orbital has a specific set of energy associated with it. And if when we define an orbital, we just say that an orbital is basically a space where there's a high probability of finding an electron. So once again, we are not sure that yes, 100% there will be an atom here. It's just a probability that this is where an electron will most certainly be. So to make that a bit more easier to visualize, here we have a picture. Those like black lines, they represent the orbits. And remember, orbits are basically, this is what Niels Bohr told us. He said that these are the fixed spaces in which electrons are revolving, and they have fixed set of energies associated with them. But then Schrodinger said that we have these orbitals. Now, if you guys notice how we have like different sets of orbitals within each orbit, and that is because these are the different places in an orbit where an electron can exist. So they don't have to specifically exist on those black lines. They can exist anywhere between these black lines within these orbitals. And when we define the orbital, we just say that orbitals are the places where an electron has the most chance to be found. So that was it for this part of the unit. I will see you guys in the next one.